Yes, we discussed the details of electromechanical system previously, and as we said, we have three subsystems which are electric system, magnetic domain, and mechanical system. And the connection between the electric system to mechanical or mechanical to electrical happens with the magnetic principles. So today we will try to understand the principles and the production of the magnetic field. So production of magnetic field can be simply explained by the Ampere's law, which says us if there's a current carrying conductor, that will create a magnetic field around the conductor. So how can we explain this? So we have a simple conductor. So if we start to flow a current, there will be a magnetic field around this conductor. And we can show this magnetic field effect with H, and we will define this H as magnetic field intensity. How the magnetic field production will be used in a magnetic circuit? So to understand this, let's analyze a simple magnetic core. We have a three-dimensional ferromagnetic core shape. So this magnetic core will be used to transfer the magnetic field from one point to another. So in this drawing, let's say we have a winding in one leg to start the magnetic field process. So there will be a current flow here. The system starts to operate with the voltage supply. And then, according to Ampere's law, this current will produce a magnetic field intensity around the conductor. So around the conductor, we can see the effect of magnetic field intensity, which is H. Then, because of the material of the ferromagnetic system, magnetic core, we can transfer this inside the core structure as B, which is magnetic field density. And then it can be transformed through the magnetic core by flux. So we can see the flux and the system flows through as phi. So let's try to make a connection between these parameters. So for H, as we said, it is the magnetic field intensity, and its unit will be ampere turns over meter. So actually it's obvious from the unit. We can write the description. For the simple analysis, H times L represents the mean path length. In the drawing, red dashed line represents the L also. And H, as I said, magnetic field density. And on the right side of the equation, we have total production. So in our figure, we have only one winding, but in some designs, we can see more than one, and we have to use total, by considering their polarities, total supply for the right side of this equation. So for this dashed line, also we can say it represents the mean path length. Why we prefer to use mean path? Because according to our assumptions in the magnetic circuit calculations, flux flow through the middle of the core, not the corners, not the around of the core. So most of the flux will flow through the middle of the leg. So because of this, we will use mean path length distance for the flux way inside the magnetic core. And of course, the unit must be meters in the calculations. And in addition to that, after H, we must transfer to B, we need to go through the magnetic core. So because of this, the new term must be magnetic field density, which has the unit of Tesla, and the relation between B and H will be B nu times H. What is nu? Which represents the magnetic permeability of the material. And we cannot find the magnetic permeability of material from the data sheets easily. So we have one subparameters more. So what is it? So nu represents the magnetic permeability of material, and its unit will be Henry per meter. And also for the nu, we must define our nu r and nu zero. What are they? For nu r, it is the relative permeability, and each permeabilities are defined based on the nu zero. So we know the relative permeability, and according to nu zero, which represents the permeability of the free space, we know how much greater value we have, how much greater permeability we have for the material. So nu zero, it shows the permeability of free space. And because of the relative term, nu r is a dimensionless parameter. So for the free space permeability, we have again Henry per meter unit. And it has a constant value, 4 pi 10 to the minus 7 Henry per meter must be used for the nu zero in the calculations. So for the relative permeability, if we give some examples, for example, for air, its relative permeability is 1. So because of this, in some references, briefly, permeability of the air is defined as 4 pi 10 to the minus 7, but air permeability is equal to 1 because its relative permeability with respect to free space is 1. They are equal to each other. For copper, it's equal to 5. For iron, it's equal to 5,000. So according to your material, you have different parameters. And in terms of your losses, which affect the magnetic losses inside the magnetic core, we need to consider about this relative permeability value further. But before this, let's try to understand the relation between B and H in detail. So for this one, we need to analyze the relation between BH by using the magnetization curve. Magnetization curve shows this relation, and we have a nonlinear behavior between B and H. And we have two regions. According to knee of the curve, we have on the left side linear region, and during this linear part, the variation between B and H is constant. But after that, you can increase the H. How? If we turn back to first equation, you can increase the H by increasing I, the current. So you can increase the current step by step, because other parameters will be constant for a specific system. You can increase the current step by step, and you can see the H also will increase. But during that time, we can see a very small change in B. So that means the maximum potential magnetization has applied to the magnetic core. So we shouldn't exceed this knee point during the continuous operation. Because after that, we have the saturation part, and during that part, the temperature of the magnetic core will increase. So because of this, we prefer to operate our core, magnetic core during that part. Near to knee, but before the knee, during the linear part, we want to operate our systems. Okay, our process started with voltage, then we produced the current according to Ohm's law, then Ampere's law has been activated to create the magnetic field intensity, and we use the permeability relation between B and H. Now we should transfer this magnetic field through the magnetic core. How we will do this with flux term. So flux, it is defined as B times A. B, it's the magnetic field intensity, and the cross-sectional area is the A in meter square. And this is the flux. The unit is Weber. Okay, so through the core, we have flux in each part of the system. And in addition to that, this part represents the cross-sectional area of the magnetic core. So for the calculations, we will go in detail how can we determine the cross-sectional area, and according to shape, how it will be important. But for now, let's try to create an analogy between the electric circuits and magnetic circuits. Because, for this figure, we have a three-dimensional system. So how we want to analyze this? To make any voltage or current calculation, we must analyze the circuit by using some components. And we prefer to use some passive components to be able to easily analyze these systems. So for the magnetic circuit analysis, let's try to compare the electric circuits and the magnetic circuits. So if we remember the electric circuit with similar topology, we have, let's say, in a simple circuit, we have one voltage source and one resistance. So this voltage source and the resistance, let's say they are connected like this. And as we know, there will be a current flow from the voltage source to the resistance. And we can write simply from the Ohm's law, V is equal to I times R, or in the opposite direction, we can write also for the equation, we can rewrite it as I is equal to V over R. So we know that part. What about the magnetic circuit? So for the magnetic circuit, if we create an analogy between them, first of all, we have also a source. Why? We have a winding in any point of the core. We have a winding, and the process will start this winding source. So because of this, our voltage source will be transferred to magnetic system, magnetic circuit source, and we will define it as a magnetomotive force. And because of the supply parameters, number of turns and I, their multiplication give us this magnetomotive force value. Okay, what's next? I, the current. When we examine our operation, instead of current, flux rotates through the magnetic core. So flux will be the equivalent of the current in the electric circuit. What else? The resistance, our third and last parameter, the simple electric circuit. So resistance also has a similar component in the magnetic circuit because it has the system. Magnetic circuit also has an magnetic resistance effect. So we will define as reluctance. So according to that, we have a source, we have flux flow through the circuit, and we have a reluctance to represent the resistivity of the core. And this is the magnetomotive force, which is Ni. And we can use this analogy for the equations also. So for the right side, for the magnetic circuit, we can write similar equations of Ohm's law. So instead of V, we can write magnetomotive force, which is Ni, and it must be equal to current equivalent flux and the reluctance, which is the equivalent of resistance in the magnetic circuit. Or for the second expression, we can write, instead of I, we have flux, and we have magnetomotive force divided by the reluctance value. So for the magnetic circuits, these equations, by using this analogy, can be used for the calculations. Okay, we have magnetomotive force, and which is very clear, N times I coming as supply, and then phi. For phi, we have some sub-equations. Until to now, we discuss a little bit. B times A, for example, magnetic field density and the cross-sectional area. Or for B, we have an expression. But for the reluctance, we don't have any expression for now. Okay, let's try to find an expression for flux, reluctance. For the reluctance, we can start with the flux equation. Flux, which is equal to B times A. And as we know, B can be written as nu times H. And again, A will remain. Then for H, we can apply the Ampere's law expression, which is Ni over L, and finally A. Okay, let me rewrite this expression. Phi, which is equal to Ni nu A over L. If you compare these two equations, and if you remember F is equal to N times I, we can say from here reluctance will be equal to L nu A, right? So we have here 1 over R, 1 over reluctance value. So this is the reluctance expression which we will use in the calculations. And in addition to this, we can follow the relations in the electric circuits and the magnetic circuits in the calculations of the total reluctances in the circuits. For example, for the series connected reluctances, our equivalent will be R1 plus R2 plus, it can continue. For series connection, our equivalent will be R1, R2, and for parallel connection, our equivalent 1 over our equivalent will be 1 over R1, 1 over R2. As we know from the electric circuits, we can still apply for the magnetic circuits. And lastly, let's make some assumptions to simplify the calculations. So the assumptions in the magnetic circuit calculations are based on the simplicity and to make the calculations clear for us. For example, the first one, all the flux is confined within the magnetic core. So that means in terms of assumptions, the first one will be related with the flux, and we will assume there is no leakage flux. All the flux are inside this magnetic core. And the second one, it is about the magnetic mean path length, and also for the cross-sectional area. So we will assume they are constant. But when we examine the flux way go through the magnetic core, the mean path length in the practical applications can change. The flux can go through the corners or inside internal points of the core. But we will assume, as we drew previously, core mean path length follows directly the middle points of the core for all way. Another one about the permeability. For the permeability, again, we will operate the systems in linear region, so we can assume the permeability will be constant during our calculations. And the last one, it's about the air gap cross-sectional area. So in the practical applications, again, for the air gap cross-sectional area will be larger than the cross-sectional area of the core because of the fringing effect of the flux. So when we examine an air gap simply, so flux will come through here, let's say, then it cannot pass through the other side directly. So the area will be bigger during this transfer from up to down. So in terms of assumptions, this bigger air gap cross-sectional area can be neglected, and air gap cross-sectional area can be accepted as equal with the core cross-sectional area. So according to examinations, if we follow all these assumptions, the difference in the calculations will be only 5%. And we will try to understand the air gap issue because it's mostly affected calculations in our some examples. Okay, thank you for watching.